In continuation of the last video on mechanism of organic reactions of BSc Part 1 Organic Chemistry, continuing the reactive intermediates, first here we will study carbanion. Chemical species carrying a negative charge on carbon atom is called carbanion. In this species, the carbon atom carrying the negative charge has 8 electrons in its valence shell, out of which 6 form 3 covalent bonds and 2 form lone pair of electrons. The stability of carbanion is believed to be due to the presence of a formal negative charge upon them. Generation of carbanions. Carbanions are found by heterolytic cleavage of a covalent bond in which the leaving group departs without the bonding electrons of the covalent bond. Every carbanion has one lone pair of electron which it can donate. Therefore, carbanions may be regarded as Lewis base or nucleophiles. Classification of carbanions. Carbanions are classified as primary, secondary or tertiary according to the carbon atom which carries the negative charge, whether it is primary, secondary or tertiary in nature. Methyl carbanion containing only one carbon is however regarded as a special case. Now we come to the orbital structure of carbanion. The structure of simple alkyl carbanion is usually pyramidal, just like that of ammonia. The carbon carrying the negative charge is sp3 hybridized. 3 of the 4 sp3 hybridized orbitals form 3 sigma bonds with atoms or groups, while the fourth sp3 orbital contains the lone pair of electrons. Since the lone pair bond pair repulsion are expected to be greater than bond pair repulsion, the bond angle in carbanion are much less than the regular tetrahedral angle. In other words, carbanions do not have the regular tetrahedral geometry but have pyramidal structure in which the bond angles are in between 97 to 100 degree. If we consider their stability, then we see that like carbocation, stability of the carbanions can be easily explained on the basis of the inductive and resonance effects. First, let's consider inductive effect. The stability of the simple carbanion follows the following sequence. Methyl carbanion is more stable than ethyl carbanion, which is more stable than isopropyl carbanion, which in turn is more stable than tert-butyl carbanion. So we see that the methyl carbanion is the most stable and tert-butyl carbanion is the least stable. The order is exactly reverse of that of carbocation, which we discussed in the last video, and the free radical, and can be easily explained on the basis of inductive effect or as we are going to discuss below. Due to the electron releasing inductive effect of alkyl groups, the intensity of the negative charge on the central carbon atom carrying the negative charge increases. The intensification of negative charge leads to the destability of carbanion. Evidently, greater the number of alkyl groups attached to the carbon atom bearing the negative charge, greater will be the intensification of the negative charge and hence more unstable will be the carbanion. Now we come to the type of hybridization effect on the stability of the carbanion. The relative stability of the carbanion from alkenes and alkanes can be explained on the basis of the type of hybridization of the carbon carrying the negative charge. For example, sp hybridized carbanion is more stable than sp2 hybridized carbanion, and sp2 hybridized carbanion is more stable than sp3 hybridized carbanion. It is seen that as the S character of the carbon carrying the negative charge increases, the stability of the carbanion increases since the electrons are closer to the nucleus and hence of lower energy. Now we consider the third effect, that is the resonance effect. The resonance effect in which the carbanions in which the unshared pair of electron is present on the negatively charged carbon is attached to a multiple bond or a phenyl group, they are more stable than simple alkyl carbanions. This is the reason that the carbanions are more stable by resonance. If we consider the stability of allyl and benzyl carbanion, we see that in this allyl carbanion, the electron pair of the double bond shifts on this carbon, creating a negative charge, and the electron pair of the negative charge carbon shifts between the carbon and carbon, forming a double bond. Thus, the carbon bond migrates with the migration of the negative charge, resulting in resonating structures. Now we consider the resonating structure of benzyl carbanion. In the benzyl carbanion, the negative charge is outside, and this lone pair is shifted between the methyl group and the carbon of the benzene group and forms a double bond. So this double bond shifts on this carbon atom, forming a negative charge, and this negative charge which has been developed within the ring migrates within the ring, forming different resonating structures, because the negative charges are different positions and hence resonating structures are formed. Now we come to the next reactive intermediate, that is carbene or methylene. Carbene or methylene is a short-lived divalent carbon species with 2 electrons. It is electron deficient and contains 6 electrons in its valence shell. It is a powerful electrophile. For example, methylene and dichlorocarbene. Carbenes can be formed in the following methods: from decomposition of diazomethane, from the decomposition of ketene. From elimination, chloroform reacts with hydroxide to form CCl3, and this CCl3 then eliminates one chloride ion to form dichlorocarbene. Or by the splitting up of 1,2-diphenylepoxyethane, this splits to give benzaldehyde and benzyl carbene. Or when methyl iodide reacts with zinc, then zinc iodide is formed and carbene is formed. Sixth method is when gem dihalides react with active metals like lithium, then carbene is formed and lithium bromide is eliminated. If we consider the decomposition of diazerenes, then diazerenes decompose to give carbene and nitrogen. Now we come to the types of carbenes. There are 2 types: singlet carbene and triplet carbene. Singlet carbenes, if both unshared electrons are group present in one orbital, then it is known as singlet carbene. Carbon is in the state of sp2 hybridized state. If we consider triplet carbene, then if both unshared electrons are present in 2 orbitals, then it is known as a triplet carbene, and here the carbon is in the state of sp hybridized. Addition of singlet carbene is cis to trans butene is an stereospecific and regioselective. For example, addition of chloroform to cis and trans to butene in presence of potassium terbutoxide. In the presence of potassium terbutoxide, cis to butene adds carbene to form cis product, and trans to butene adds one product CCl2 to form trans product. But addition of the triplet carbene is a biradical addition to carbon-carbon unsaturation. So when cis to butene is reacted with triplet carbene, then mixed product of cis and trans product are formed, and when trans butene is made to react with carbene, then also mixture of cis and trans products are formed. If we consider the mechanism, then we see that in the addition of singlet carbene to the alkene, the double bond breaks, the pi bond breaks, and 2 new sigma bonds are simultaneously formed, and there is no chance for the carbon-carbon bond to rotate. Therefore, it is stereospecific. Now we consider the triplet carbene. It is not stereoselective, because when we see the addition of the carbene, then first split homolytic cleavage of the double bond takes place, and at one carbon the addition of carbene takes place, forming a intermediate. Now this intermediate can react in 2 ways. Now since the CC bond is single, it can rotate. So if it rotates, then a rotating product is formed, and that this rotated product then forms a bond and with carbene, and trans derivative is formed. But if this intermediate which was formed by the addition of by forming one bond with carbene does not rotate, then another bond takes place and cis derivative is formed. That's all for today. Thank you.